Alright, so this problem says find the volume of the solid generated by revolving the region bounded by the given lines and curves about the x-axis. We're told that y equals x, y equals 0, x equals 1, x equals 5. Now remember, I told you anytime you say y equals 0, that's the x-axis, right? Because that's where that graph would be. Anytime you see x equals 0, that's the y-axis. And the problem did say that we want to revolve this region about the x-axis. That's important. Okay, so let's do a rough sketch here. Alright, so we have y equals x. That's really easy to graph, right? Because that's a y-intercept of 0 and a slope of 1. So just about the easiest graph you could possibly do there. There's a rough sketch. It's supposed to go through the center there, and its slope is 1, so that means when you go up 1 on the x, you go up 1 on the y. Alright? Then we have y equals 0. Again, that's the x-axis. So that's this graph here. Then we have x equals 1. So let's put us a couple of tick marks here. Here's where x equals 1. So my scale is pretty small here, so you can see our bounded region is starting to form. And then x equals 5. So I might have to put a few more tick marks here. So I might have to count out 2 more. Okay. I'm also going to extend my graph y equals x. So 1, 2, 3, 4, 5. Here's where x equals 5. Okay. So at first, before I drew everything, I was thinking this was the region, because that is a bounded region. However, because we have x equals 5 in here also, then the bounded region is this region here. So this is the region where all of our rectangles would be formed, which then we would revolve about the x-axis to give us discs. So we're going to, and if you need to kind of put a little visual there, we're going to form these rectangles, these vertical rectangles, and it's an infinite number, so there's not going to be any space in between them. And every one that we form, when we revolve it about the x-axis, is going to form a disk. Okay? Each one has a width. We'll just call that's our delta x. Since we're gonna sum up an infinite number of those, our delta x, our width, is approaching 0. It's not 0. Okay? Otherwise, we wouldn't have a volume. But we're going to sum up an infinite number of those. And when we do, roughly, we're going to have some figure that's going to look something like this. And so all of this, if you could imagine that this was in 3 dimensions, which it's in 2 dimensions, but all of this is going to be a solid figure. So what kind of figure would that be? Well, since it has a flat bottom, maybe it looks, if you look at it from the side, maybe it would be like a bowl of some sort. It would be solid, though. It wouldn't have a hollow inside, so you couldn't put anything in it. But it would be, I'm sure it would be some type of usable figure somewhere. Maybe a stand. Maybe if we look at it from this side, This is our stand here that's solid. We're going to put us a little math trophy up here because we're all math winners, right? All right, so it will be a solid figure, and that is what it would look like in 2 dimensions. So we want to figure out the volume of that figure. Maybe we need to know how much material we need in order to carve out that figure. Who knows? Or maybe we have a set budget. We want to know, can we buy gold? Can we buy silver? Do we have to buy copper or brick? I don't know. Anyway, so what we want to do, we just want to think about this in 2 dimensions at first, and we want to think about the height of each one of these rectangles, which in turn is going to be the radius of the disk. I know I'm going really slow, but sometimes if you don't revolve about the x-axis and you revolve about a line, you have to be able to sketch and understand what you're looking at, because the radius can change sometimes, and the way that you set up the problem can change sometimes. So if you do have any questions, make sure that you ask. Anyway, so we're forming an infinite number of these rectangles. We're revolving them about the x-axis here at y equals 0. And when we do, we're going to have that solid figure, and it's going to be awesome. Okay? So what will the radius of each disk be? It will be the height of the rectangle. So how do I get the height of each one of these rectangles? You plug an x in and then come over to the y-axis, and that will tell you the height, right? For any value. Let's say that I had, I know that it's an infinite number, but let's just pretend that this was an infinitely small width here, and we had this disk that was going to be formed. Well, if I want to know the radius of that disk, then it's going to depend on this curve here, because whenever I plug in, say, x equals 3.5, that's going to give me the height. If I plug in the x, I get out the y, and the y gives me the height. So in this problem, the height of each disk, or the height of each rectangle, is going to depend on this curve. All right? So our capital R of x is going to be equal to just x, right? Because this was y equals x. So it's just going to be x. All right, so now let's plug it into the formula. Volume equals pi times the integral. What are our x-intercepts? 1 and 5. See right here? That's x equals 1. That's x equals 5. And then we have of r of x squared. So r of x is just x. Sometimes it might be a binomial. Sometimes it might be a quadratic. On this problem, it's simply x. All right, so we have x squared here. The integral of x squared is going to be x cubed over 3. I want to evaluate that from 1 to 5. And remember, we have that pi in front. That's our constant that we have to multiply it by. And the reason there's a pi in front is because of the formula that we have to use to find the area, the volume, right? The area, but then in turn the volume of each disk. So this is going to be pi times, plug in the 5, you have 125 over 3, minus plug in the 1, you have 1/3. So that's pretty easy there. pi times 124 over 3. So 124 over 3 times pi. We don't want decimals here. We don't want rounding here. We want to leave answers exact. So this is the volume. 124 over 3 times pi. All right, let's look at the next problem. The directions are the same. We have the graphs y equals the square root of x, y equals 0, x equals 0, x equals 9. All right, so let's do a rough sketch here. I'm going to have to go all the way out to x equals 9. All right. So what happens with y equals the square root of x? As x increases, we take the square root of that x, and that gives us the y. So, if x is 0, we're right here at 0. If x is 1, we're right here at 1. But then if x is 2, the square root of 2 is about 1.41. If x is 3, we have the square root of 3. And so this is going to increase. I guess we could use some whole numbers to help us that we can take the square root of. Like at x equals 4, we're at 2. And then at x equals 9, we're at 3. So you can see this curve does increase forever, but it increases a little slowly here. Right? So we have that curve. We have y equals 0. We have x equals 0. And we have x equals 9. I think that I made 9 out here, and it's supposed to be about right here. But you get my drift. It's supposed to be right here. It's supposed to be 3. All right? So there's y equals 9. All right, so the bounded region here is going to be this in here. And whenever we take an infinite number of those disks and revolve about the x-axis, then it's just we can make a reflection here. We're basically going to have a shape like this. Maybe it kind of looks like a bullet or something like that. Or I don't know, just something similar to that. But it would be in 3 dimensions there when we revolve those rectangles. Now we don't have to have this picture. We don't have to have the whole picture. Sometimes looking at the whole picture may confuse you a little bit. We really just want to look at this thing in 2 dimensions to help us figure out the radius of each disk. Now on this problem, again, since we are bound by the curve and the x-axis, the height of each disk is just going to depend on this function. Whatever x you're at, the height of the disk, or the radius of the disk, you would go up to the function, you plug it into the function, and it gives you the height over here on the y-axis. All right? So our capital R of x, our radius, is going to be the square root of x. So our volume is going to be pi times the integral of the square root of x squared dx. And our boundaries, our x-intercepts, are 0 and 9. All right, so we have pi times the integral of just x. So that's going to be pi times x squared over 2, evaluated from 0 to 9, or pi times 9 squared over 2 minus 0 squared over 2. So 9 squared, that gives us 81. So our volume is going to be 81 over 2 times pi. All right. Now, look at the next problem. Problem number 3 here is a little different. The directions stay the same, but we're revolving about the y-axis. Okay. So it says that we want our region to be enclosed by x equals y to the 1/3, x equals 0, y equals 8. Now, if you do need to have y equals x to help you sketch, how would I make this y equals x if I wanted to? You cube both sides of the equation, right? If you cube both sides of the equation, then you would have y equals x cubed. So this graph is going to be the same graph as y equals x cubed. If you do still need to think about this like y equals x, you know, you can use that to help you sketch the graph. You can see that as x increases, y increases really fast because it's being cubed. So, for example, when x equals 1, y may be equal to 1, but when x equals 2, y is equal to 8. So it's way up here already. So this graph goes up like this, and then it goes down like that. X equals 0 is the y-axis. So it's that line there. And then y equals 8. I mean, I have the best scale here. But there's y equals 8. So this bounded region in here, that's what we're going to be revolving about the y-axis. And you can see when I do, it's going to make another one of the shapes just like the last problem. Maybe like, I don't know, half of a peanut or something like that. But it may be a lot larger than that. So just something in that shape. Now, remember what we're doing here to form discs. That's very important. We're taking, before we were taking vertical rectangles. Now we're taking horizontal rectangles, an infinite number of those horizontal rectangles. I'm just spacing these out to show you a finite number, but it's an infinite number of those to make discs. Okay, so again, to find the height here, do you remember what we did when we were finding the area between two curves? We would say right minus left. Well, the right curve minus the left curve, that's going to be, this is y to the 1/3 power minus 0. That's what we were actually doing before. We were just saying, like on this problem, the square root of x minus 0. That gave us the height of the rectangle. I didn't say minus 0, but since we're bounded below by that axis, that's what we're actually doing. So here, our r of y, which is the radius of our disk is going to be equal to y to the 1/3. Okay, so our volume, now remember when we have x equals y, and we have that with the disk method if we have a vertical axis of revolution, which we do here, we have to use y intersection points instead of x. So the volume here is equal to pi times the integral of y to the 1/3 squared dy, and our intersection points, we're using y intersection points, are 0 to 8. All right, so this is pi times, well, let me do one more step before I integrate. I don't want to lose anybody. So this is the integral from 0 to 8. When you square y to the 1/3, power to a power, you multiply. So that's y to the 2/3. And we're integrating with respect to y. All right, so what is that going to be? Add 1 to the power, you would get 5/3. Divide by the new power. So it's y to the 5/3 divided by 5/3, or 3/5 y to the 5/3. Now what I would suggest doing, just to make our calculations a little bit easier, take this constant in front and move it out. So in front we have 3/5 pi, and then we're going to evaluate y to the 5/3 from 0 to 8. All right, so we need to understand what 5/3 means, the 5/3 power there. Remember, the bottom number is the index. So this means the cube root of 8, the top number is the power. You can either put the power under the radical, which I do not suggest doing. 8 to the 5th is a big number. Or what you can do is you can put this in parentheses and put the power on the outside. That's what I suggest doing, because we can take the cube root of 8 and then raise that to the 5th. All right? So then minus, we plug in a 0, 0 to the 5/3 power is 0. All right, so let's see what we get. We got 3/5 pi times 2 to the 5th power. What's 2 to the 5th power? All right, 32. So 3 times 32, 96. So this is 96 over 5 times pi, cubic units. That's the volume of the solid that would be formed if we revolve that region about the y-axis. Now, sometimes when we revolve a region about a line, it's not the x-axis or the y-axis. You know, we can just revolve it about a line. It doesn't have to be one of the axes. Now what that's going to do is that's going to change the way that you figure out the radius of the disk. When you revolve about a line other than the axis, it generally changes the way that you figure out the radius of the disk. If you can graph it, and it will help you understand a lot better. Okay? So let's look at this problem. All right. So this is out of your ebook, page 448. It says, find the volume of the solid formed by revolving the region bounded by the graphs of 2 minus x squared, g of x equals 1 and y equals 1. Oh, I'm sorry, about the line y equals 1. Okay. So first we have to be able to graph that. We know that it's a parabola because of the x squared, or a quadratic graph. Since the x squared is negative, we know that it's opening downward. Okay? What I would do from that point is I would figure out where are the x-intercepts and where is the y-intercept. So if I let x equal 0, y equals what? 2. Okay. So we're going to say we know that this graph is going to cross here at y equals 2. Now, how do I find the y-intercepts? I set x equal to, no, I just found the y-intercept. How do I find the x-intercepts? I set y equal to 0 and solve. So if I do that, I'll get 0 equals 2 minus x squared. So x squared equals 2. So x equals plus or minus the square root of 2. So the square root of 2, remember I told you, was about 1.41. So we know that we're going to cross the x-axis around there, and we're going to cross the x-axis around there. So for a rough sketch, this right here looks fantastic. All right, so we have our quadratic opening downward, and we know those intersection points are right. Now, it also says that we are bounded by g of x equals 1. So basically, that's just y equals 1. So this line right here, that's y equals 1. And then it says about the line y equals 1. So this line that we just drew, that's going to be our axis of revolution. We're going to revolve this stuff right here. It's in here. We're going to revolve that about this line. And so the way that we calculate the height of each rectangle, which in turn is the radius of each disk, is by taking the difference in the top curve and the bottom curve. I'm just going to draw a couple of rectangles up here to show you, each time that we take this rectangle and we revolve it, it's just reflected about that line and it makes a disk. So you can see the radius is going to change according to the height of the rectangle. The height of the rectangle is simply the top curve minus the bottom curve. Right? Whatever y value that we get out whenever we're here, so whatever y value we get out here minus the y value here will give us the distance between the two. All right? So what is our radius of each disk, or the height of each rectangle, going to be? Top curve minus bottom curve. What's the top curve here? 2 minus x squared. Minus, what's the bottom curve? Y equals 1. Top curve minus bottom curve. That gives us the height of each one of those rectangles, which in turn is the radius of each disk that we make. So you can go ahead and simplify that. We have a 2 minus 1, so we get 1 minus x squared. That is the radius of each disk. So that's what we use in our integral. So volume equals the integral, or pi times the integral of 1 minus x squared squared dx. Now we have to figure out the boundaries. The boundaries are going to be the intersection points. So from here to here. Now don't always trust your eyes. Okay? I'm sure I didn't graph this to scale. So how do we figure out those intersection points? We set the two equations equal and solve for x. So 2 minus x squared equals 1. So if you move the 1 over, you move the x squared over, you flip it around, you have x squared equals 1. Solve for x, you get x equals plus or minus 1. So this point right here, you see why I said don't trust your eyes. This is x equals 1. This is x equals negative 1. Okay? So we integrate from negative 1 to 1. Now, don't do like the bad student would do and square that binomial by just squaring the first term and the second term. That doesn't work. You have to FOIL that out. You have to say 1 minus x squared times 1 minus x squared. Okay? So that's going to be 1 minus 2x squared plus x to the 4th after you FOIL that out. All right, first outer, inner, last. Combine the like terms. So then we can integrate. So that'll be x minus 2/3 x cubed plus x to the 5th over 5. We're evaluating that from negative 1 to 1. Alright, so plug in a 1. We have 1 minus 2/3 plus 1/5. Minus, plug in a negative 1. We have negative 1. And then when you cube negative 1, you're going to get a negative 1 times negative 2/3. It's going to be plus 2/3. And then when you raise it to the 5th power, that's going to be a negative 1/5. Now, whenever you put all of these numbers together and subtract, you're going to get 16/15. So your answer is going to be 16/15 times pi.